Let's look at an example where we use the central limit theorem. Suppose that we have 120 different variables that are all independent. Let's call them x1 up until x120. All these variables are independent, but they all have the same distribution. And that distribution is given by this density function right here. What is the question that we want to solve? Well, you see it here in green. We want to find the probability that the sum of all these variables is at least 45. And well, we're going to use the central limit theorem for that. You see the theorem that we're going to use here on the screen. This theorem tells us that if we have a bunch of variables, all with the same distribution and independent, then if n is large enough, then we can approximate the sum of all these variables with a normal distribution. So, well, let's use that theorem. If you read this theorem, you see that we need two things, the expectation of our variables x and their variance. Well, right now we only have the density function, so we need to compute the expectation and the variance. Of course, the expectation is quite easy to compute, especially if the density function is rather simple, which is the case here. The expectation is the integral from minus infinity to plus infinity of f times the density function dx. So right here we get x times 2 times y, 1 minus x dx, and we can use the boundaries 0 and 1 because whenever x is smaller than 0 or larger than 1, then our density function is 0 anyways. So this is the integral that we need to compute. Quite a simple integral. If you would solve it, you would find 1 over 3. And so that's the expectation of the variable, well, of all variables, x1, x2, up until x120. Now the variance. Well, we already have the expectation, and hopefully you recall that the variance of a variable is the expectation of x squared minus the expectation of x squared. We already know what the expectation of x is, so we just need to compute the expectation of x squared. Well, and actually that's very similar to computing the expectation of x, because in this case we can multiply x squared with our density function and then integrate once more from 0 to 1. If you would compute this integral, you would find an expectation of x squared of 1 over 6. Okay, so this means that we can find the variance. The expectation of x squared is apparently 1 over 6, and the expectation of x we already computed, that was 1 over 3. So what do we find for the variance? 1 over 6 minus 1 over 3 squared, and that's equal to 1 over 18. Now the theorem that you see here on the screen tells us that the sum of all these variables, x1 plus x2 plus x3 up until x120, the distribution of this sum can be approximated with a normal distribution. And in fact, we get a normal distribution with expectation n times the expectation of x, so it means 120 times 1 over 3, which is 40, and a variance of n times the variance of x, so that means 120 times 1 over 18. 120 over 18 can be simplified and is equal to 20 over 3. Now we can go back to our original problem, the probability that the sum of all these variables is at least 45. Well, now we know that we can approximate the distribution of this sum with a normal distribution, so we can use that to compute this probability by applying the usual trick, and it's making everything standard normal. So what are we going to do? Well, minus 40 and divide by the root of 20 over 3. Because if we do that, then we get a new variable with a standard normal distribution. So the variable on the left, we will denote as z because it's custom to denote a standard normal distributed variable with a z. And on the right-hand side, we get 45 minus 40 over the root of 20 over 3. If you would compute this value on the right-hand side, you would find 1.94. This particular probability we can find using a standard normal table. So you see one over here. How do you use such a table? Well, so the values that you see here are actually probabilities that z is at least a, where z is a standard normal distributed variable and a certain number. And just to be clear, these values that you see here are the 4 decimals. So for example, this 0.694 is a probability of 0.0694. We wanted to compute the probability that z was at least 1.94. Well, we can find the first part of that particular value here, 1.9, and then we look in the top row for the second decimal, the decimal 4, and that's over here. So that means that the probability that we are looking for is equal to 0.0262.